Okay, so this is a review of homework 8, which is on the semantics of predicate logic. As you know, if you did the homework, the semantics of predicate logic work a lot differently than the semantics of propositional logic. In propositional logic, we're able to just use truth tables. But in predicate logic, we have to do something more complicated, and that is that we have to use models. Now, it's really not true that you can't use truth tables at all for predicate logic. If we have, for example, a predicate logic formula like FA or GB, throw a negation in there for fun, you could run a truth table on this just fine, right? You just write FA, GB, true, true, false, false, true, false, true, false, and fill it out the rest of the way, and you'd have all the truth conditions and therefore a full interpretation, meaning a specification of the truth value for this proposition for all possible assignments of truth values to the atomic propositions. But when we introduced quantifiers and variables, it starts looking a little different. So for example, if I wrote for all x, there exists a y such that it's not the case that fx or gy, this is just one proposition which can be either true or false. So truth tables certainly don't have the power to characterize the logical complexity of a proposition like this. And just to make that clear, if you took a proposition like if P then if Q then P in propositional logic, you could use a truth table to show that that's a tautology. But here's another tautology for all x, if f of x, then if g of x, then f of x. But a truth table can't show that this is a tautology, so we need another way of approaching it. So a tautology, as you'll remember, is just a proposition that is true under all possible interpretations. And in propositional logic, that just means true on every line of a truth table. So to preserve that notion of a tautology, we need a different characterization in predicate logic. And so we've invented this notion of a model. And a model is a structure in which the predicates and the names are given specific interpretations by attaching them to particular objects in the model. And so in predicate logic, when we say that a tautology is a proposition that is true under all interpretations, what we mean is that it's true in all possible models. So what we're working on today is just seeing what it's like to interpret predicate logic formulas within a particular model. So let's go ahead and take a look at how that works. Okay, so in formal logic, it's not necessarily all that common to use pictures when specifying a model, but it makes things a lot easier than either writing things out exhaustively or depending on general world knowledge. So what we're looking at here is just a picture of chess pieces lined up in a particular way. So king, queen, bishop, knight, rook, and pawn from left to right. And that is our universe. In every model, you specify a universe, or what's sometimes called a universe of discourse. And so our universe is just these chess pieces lined up in this particular geometrical fashion. So beyond specifying a universe, a model also requires you to say what the names of the objects in the universe are. It doesn't actually require you to give every object a name, but the semantics of predicate logic requires that every name you acknowledge attach to one and only one object. So here I've adopted the expedient of naming each piece, the name of the type of piece that it is. So the king being a property, though we'll get to that in a second, is actually named king. The queen is actually named queen, or little q. The bishop is actually named bishop, or little b, etc. And then we've identified several predicates. There's the property of being a king, the property of being a queen, the property of being a bishop. Knight, we use n instead of k, since that's already been designated for king, etc. And then we designate the colors, D for dark and L for light. Now, you don't have to have any particular type of predicate in a model. That's totally your choice, but I've gone ahead and used both one-place predicates and two-place predicates. So of the two-place predicates, we have S for stronger than, W for weaker than, and E for equal in strength to. And then we also have T for taller than, and A for adjacent to. And adjacent means next to, directly next to. And then we've gone ahead and explicated this notion of strength in this table below. This is not a common aspect of a model. We just need it for clarification. So we've said that the pawn has strength of 1, which is the lowest strength. Knight has strength of 3. The bishop has strength of 3. The rook has strength of 5. The queen has strength of 9. And we're going ahead and said in the specification of the universe that the king is infinitely strong, or has infinite value, because of course in chess, if you lose the king, you've lost everything. Okay, so any model you'll ever encounter will be of this kind, or at least satisfy these basic features. Specification of a universe, specification of names, all of which must name an object in the universe, and then a specification of predicates. Now, what the picture does is that it actually tells you which objects instantiate which predicates. So you can actually simply see that the knight is light and the rook is dark. If you couldn't see that, we would actually have to write that down as well. And just remember, we're only talking about this picture. Our universe is this picture. It's not all of the chess pieces on a board, because if we got that complicated, then of course there would be a light knight and a dark knight, etc. Okay, now the assignment here is quite simple. You're simply required to evaluate each of these formulas as either true or false in this model. But the really important skill that you need to develop is to say why. Effectively to give a proof that your answer is correct. Now, I don't require you to do this in the homework, but I do give it in the homework solution, and that's what we're really going to focus on in this review. So unless you can do that, you're really just guessing. The other thing that you really need to work on here is saying these formulas out loud. You don't just want them to be sort of a thing on the paper. You want it to be something that you own and really understand. And a huge amount of that is just being able to pronounce them. So work on that while we do this too. All right, so the first one says king is king, or if rook is king, then queen is a knight. Okay, so the king is a king, or if rook is a king, then queen is a knight. And you need to evaluate that as true or false in the model. Now, how do you do that? Well, this is a disjunction. And so you know that a disjunction, and here we actually do refer to the truth tables, a disjunction is true whenever one of the disjuncts is true and false otherwise. So if one of these disjuncts is true, this proposition has to be true. The first disjunct says that king is a king, and that is true, right? So that's all you need to know. You don't have to look at the conditional, right? It's true because one of the disjuncts is true. Now the second one is a conditional, and I hope you see that the conditional is actually logically equivalent to the disjunction, and that makes it true simply because it's logically equivalent. If you didn't happen to notice that, you would say, okay, this is a conditional, and a conditional is a proposition that is false if the antecedent is true and the consequent is false, and true every other time. And what that means in particular, that entails in particular, is if there is a false antecedent, then it's true. And of course, we see that it has a false antecedent because the antecedent says it's not the case that king is king, and that's false. So because it has a false antecedent, the whole proposition is true. Okay, so now let's move into some quantified formulas. The third one says there exists an x such that x is a queen and x is a rook. Okay, make sure you can read that. There exists an x such that x is a queen and x is a rook. So this asserts that some one thing is both a queen and a rook. And that is not the case. Nothing is both a queen and a rook, so that is false. So the third one says there exists an x and there exists a y such that x is equal in strength to y and x is identical to y. Now this one is very important to understand, and I'm going to stop for a moment and call up the whiteboard. Let's create a universe that consists of two dots, a blue and a red dot. Now let's consider this formula. There exists an x and there exists a y such that x is blue and y is blue. Is that true or is that false? Give me a real answer. Okay, so the correct answer is that it's true. Now, why is that? It's because there is nothing in this formula that requires x and y to be different. They can be exactly the same dot. And that's not to be tricky or anything. That's just a fact that when we use the existential quantifier twice, there is nothing in the rules for using it that requires that refer to different things, and that would be a very bad thing if we did require it. Think about this. Suppose we make the blue thing not a dot, but say a little triangle, and now we change this to there exists an X and there exists a Y, such that X is blue and Y is a triangle. This is something that turns out to be true at all, and probably true as well, and probably that's more evident to you, even if it does still seem a little awkward, because you could say, well, clearly this thing is blue and it's a triangle. So there is something that's blue and there is something that's a triangle. It might even be more obvious to you if we wrote it like this. There exists an X, B of X, and there exists a Y, T of Y. So the important thing to realize here is that if you are going to insist that they're not identical, you actually have to build that in to the statement. So if I go back to the original two dots and I write there exists an X and there exists a Y, such that X is blue and Y is red, Y is blue, and what would you add? It's not the case that X equals Y. Now that is going to turn out to be false. Why? Because by saying they're not equal, and this is something we covered in the last homework, we're saying there have to be two distinct ones. There's only one thing that's blue, not two distinct ones that are blue. All right, so this should help with evaluating the fourth formula. There exists an X and there exists a Y, such that X is equal in strength to Y and X is identical to Y. So if you read this as saying there are two distinct things, then you're going to get the wrong answer. You need to read this as saying there are two things which may very well be the same thing, such that X is equal in strength to Y and X is identical to Y. And then, of course, it turns out that this is true, right? Because everything is equal in strength to itself and identical to itself, right? So that's true. So the next one says, for all X and for all Y, if X is equal in strength to Y, then it's not the case that X is identical to Y. Now, this is a universally quantified expression. So the first universal is the main operator. And so what this means is the formula has to be true of every single thing in the universe. And then the second universal is also going to require that it be true of every single thing in the universe. Now, the expression inside the parentheses is a conditional. And whenever you're looking at a conditional, you really want to focus on what would make it false. So this statement would be false if there is two things that are equal in strength to each other. So we satisfy the antecedent condition, and it's false that they're not equal to each other. So false that they're not equal to each other would mean that they're equal to each other. So we can make this statement false if we just find something that is equal to itself, which is of course equal in strength to itself, which of course is any piece on the board, and self-identical, which of course is any piece on the board. So every individual piece on the board constitutes a counterexample to this, but you only need one, right? So you can just say, well, pawn is equal to pawn, but it's not the case that pawn is not equal to itself. In other words, pawn is equal to itself. So since pawn is equal to pawn, or pawn is equal in strength to pawn, and pawn is indeed self-identical, this turns out to be false. So the next one says there exists an x and there exists a y such that x is taller than y and y is, it's not shorter, it's stronger than x. Now nothing is taller than itself and nothing is stronger than itself, so of course in this case we're going to be looking for two separate things. We're dealing with a conjunction, right? So what we need to find in order to make this true is two objects where one is taller than the other and the other is stronger than the one. So if you look at the model, you can see that the bishop is taller than the rook. So bishop is taller than rook, and rook is nevertheless stronger than bishop. Rook is 5, bishop is 3. Okay, so that makes this proposition true. And of course the reason is because these are existential quantifiers. So it's really useful and important. I don't want to do it too often because it's going to make this excruciatingly long. But to play around with these quantifiers and see what it would do to their truth value. So for example, suppose we changed the first existential to a universal, like that. So now it says, for every single x, there exists some y such this conjunction holds. So for all x, there exists a y such that x is taller than y. Well, right off the bat, you know that can't be true. And that's because there is the shortest thing on the board, namely the pawn. So this says, now for every x, there exists a y such that x is taller than y. And that is simply not true of pawn. And both conjuncts have to be true for this entire statement to be true. So changing the universal, changing the existential to a universal, in this case, would change the truth value. What happens if you change this one to a universal? Well, now it says there exists an x such that for all y, x is taller than y and y is stronger than x. But again, from reading the very first conjunct, you can see that it is now false. But maybe it takes just a tiny bit more insight, right? Because we know the tallest thing on the board is the king, right? So this says there exists an x such that for all y, x is taller than y. And you might say, okay, well, that's the king. But it's not the king, is it? You know why? Because the king is not taller than itself. So since nothing is taller than itself, it cannot be true that there is something that is taller than everything. Okay, now the next formula is a biconditional, and it says the pawn is king if and only if there exists a y such that y is stronger than y. So pawn is a king if and only if there is something that is stronger than itself. Now the way you want to think about a biconditional, again by reference to the truth table, is that it's true whenever the truth values of the formula on both sides are true, or when they're both false. When they have different truth values, then the biconditional is false. We're reading that right off the truth table. Okay, so what is this? Well, we know that it's false that pawn is a king, and we know that it's false that there's something that is stronger than itself. So since both sides are false, this has to be true. Next one, for all x, the pawn is weaker than x. Now, if we hadn't been talking about the importance of self-reference here, of applying these formulas to the very thing being named, then you might be taken in by this one, but hopefully now it's obvious to you that this is false. Why? Well, because it tells us that the pawn is weaker than everything, but the pawn is not weaker than everything, because the pawn is not weaker than itself. So the next one is a biconditional. We already know the first formula is false. The pawn is not a king. What about the second expression? It's a conjunction. It says queen is stronger than pawn. That is true, but we need them both to be true if the whole conjunction is going to be true. So the second one says that the bishop is weaker than the knight. The bishop is not weaker than the knight. The bishop is equal in strength or value to the knight. So that makes the conjunction false, okay? So once again, we have false, false, which makes the whole biconditional true. Okay, next expression. There exists something that's dark. There exists an x such that x is dark. And also, okay, so we need at least one dark thing. And so the only things on the board that can make this true are the dark things, right? Knight, bishop, and rook. Everything else on the board would make this false because they're light, and so they would make d of x false, and therefore the whole conjunction false. Okay, so there exists an x such that x is dark, and then for all y, if it's not the case that x is stronger than y, remember, get yourself to say these things. So if it's not the case for everything on the board, it's not really a board, I shouldn't be saying that, for everything in the universe, if it's not the case that x is stronger than y, then x is identical to y. So in this case, you can treat it as a conditional and say, and look at everything that would make the antecedent true and see if it makes the consequent false. So for example, you could say, remember with x, we only have to think of the dark things. So you could say, okay, well, look, the bishop is dark, right? And for all y, if it's not the case that the bishop is stronger than y, so say let y be the queen, so that makes this true because the bishop is not stronger than the queen, then x is identical to y, and that's false. So if we plug the bishop in here, the whole statement is false. But does that mean the statement is false? No, because this is an existential statement, and we only need, in order for the existential proposition to be true, we only need it to be true of one thing. So let's choose the king, right? So there exists an x such that x is dark. Okay, king is dark. And for all y, if it's not the case that x is stronger than y, well, the king is stronger than everything, right? Except itself. So if we plug king in for x, then the only way that we can make the antecedent true is by plugging king in for y, but then of course that would make x identical to y. So there exists an x such that x is dark, namely the king, and for all y. If it's not the case that x is stronger than y, the only thing that satisfies that condition is the king itself, then x is identical to y. So with the king, the only thing that makes the antecedent condition true is the king itself, entailing that the consequent is true as well. Now, the other way, and possibly more obvious way to think about this, is to convert the conditional into a disjunction. So you know that not P then Q is logically equivalent to P or Q. So the other way to read this is there exists an x such that x is dark, and for all y, either x is stronger than y or it's identical to y. Can you see how that makes its truth value a little bit more obvious? Because the king is clearly stronger than everything else except itself. So either the king is stronger than anything you could name, unless you're naming the king itself. Okay, so true. Okay, and I think this way of thinking of the conditional as a disjunction is actually generally quite helpful. So we've noted already when we were doing translations how kind of peculiar existential claims are when they're expressing a conditional. So there exists an x such that if x is dark, then x is light. That might just strike you on the surface as being patently false. If something's dark, then it's not light. But now, suppose you convert that into, well, I know that means the same thing as there exists an x such that it's not dark or it's light. Well, then it just becomes patently true, right? There is something that's not dark. Well, yeah, there's three things that are not dark. So automatically it's true because it's a disjunction and only one of the disjuncts needs to be true. But if you want to explore further, there exists something that's light. Yeah, well, three things are light, the very same things. So you might be kind of going, what? I mean, can those really be the same thing? Well, you know that they are because you know the truth table for the conditional. But what you're really asking there is if we went through that same reasoning, just treating as a conditional, would we obviously just come up with the same answer? And the answer is yes, or it had better be yes. So what happens when you do that? So this is going to be made true by anything that makes the antecedent false, right? So there exists an x such that if it's dark, then it's light. Well, the pawn is not dark, so it makes the antecedent false. And any time a conditional has a false antecedent, then the conditional is true. So the pawn makes this true because the pawn is something that if it's dark, which it's not, then it's light. So true. Now you switch the quantifier to a universal, and now it becomes simpler just to treat it as a conditional, at least in my mind as it does, because this says every single thing is such that if it's dark, then it's light. So now you're just looking for a counterexample, something that makes the antecedent true, but the consequent false. And of course, every dark thing makes the antecedent true. So take the rook, and this requires that if the rook is dark, which it is, then it's light, which it's not, right? So the rook is an example of a dark thing that's not light. So answer false. Next one, for all x, if x is a bishop, then x is identical to bishop. Well, everything, every single object makes the antecedent false, and therefore the whole statement true, except the bishop itself, right? So bishop makes x is a bishop true, and of course bishop is identical to bishop. So all the things that aren't bishops make it true, and the bishop also makes it true, so the whole thing is true. All right, so the next one, for all x and for all y, remember to read these out loud, if, right, there exists, not there exists for all x and for all y, if x is equal in power to y, and it's not the case that x is identical to y. So this is a conditional, and the only thing that can make the antecedent is true is two distinct things now, right? Because they can't be identical, that are equal in power. And the night is light, right? So true, true. So the bishop in the night would appear to make this proposition true, but they don't, right? Can you see why? Well, suppose we make the knight x and the bishop y, right? So again, that makes the antecedent true, but now the conclusion is false. So because the order of x and y matter here, you get a different result depending on how you plug them in, and you have to explore both ways. So this is false because it is not true of every two things in that particular order. All right, the next one is exactly the same antecedent, but the consequent is x is a bishop or y is a knight. So once again, suppose we put the knight in for x and the y in for bishop, then it's not true that x is a bishop, and it's not true that y is a knight. So once again, this turns out to be false. Another one with the same antecedent, but now the consequent is x is dark or y is dark. And here that's going to turn out to be what? Got to turn out to be true, because no matter how you arrange the bishop and the knight, one of them has to be dark. Now, if you think about a little preface to this homework review, we talked about something that was a tautology that had the form if P, then if Q, then P. This next one has that form, except that we've got a double negation on the back end. So this actually is a tautology, and since all tautologies are true, this has to be true. And since it is a tautology, that means that you should be able to show that it's true without even looking at the model. And you can definitely do that. But let's make sure it's true in the model. So bishop is dark is true, okay, which means we need to go on. If it were false, then we'd be done, right? Then, if the king is light, well, the king is not light, so that makes this conditional true, right? So true, 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 so it's definitely true in the model. The way you do that is you say, okay, suppose DB is false. If DB is false, then the conditional is true. So we only need to examine models in which DB is true. Suppose DB is true, then LK is either true or it's false. If it's false, then the second conditional is true, making the whole conditional true, and that was the case in this model. But if it's true, then not DDB is also true because DB is true. So either way, whether LK is true or false, the conditional has to be true. So true, true, it is always true. Okay, the next one says for all x, if x is dark, then there exists a y such that it's not the case that y is taller than x. So all light things, all non-dark things, makes this conditional true. So we only have to think about the dark things and consider whether any of the dark things that make the antecedent true make the conclusion false. If one of them does, then the whole proposition has to be false. So you look first at the king, maybe, right? The king is dark, and certainly there exists a y such that it's not the case that y is taller than the king. That would be everything except the king itself. So look at the bishop, right? Bishop is dark, and there certainly exists a y that's not taller than the bishop, say the pawn. And then look at the rook. The rook is dark, and there also exists a y that's not taller than the rook, right? So all the light things make this true, and all the dark things make this true as well. So the last one in the first column, for all x and for all y and for all z, if x is stronger than y and y is stronger than z, then z is weaker than y. Now, this is something that you might want to say is a necessary truth by virtue of the meanings of stronger and weaker, and that's actually correct. But we haven't specified specific inference rules or relationships between stronger and weaker in our language that would allow us to actually prove that this is tautological. So we have to satisfy ourselves with just showing that it's true in the model. And the way you would do that is to simply say that any three things that make the antecedent false, and that of course could involve one or two things if x is equal to y or y equals z or x equals z. But we'll just say three things. Any three things that make the antecedent false make the whole thing true. So the only things we have to think of are things that make the antecedent true. And to be thorough about this, you'd actually have to just go down the list, right? So you think, okay, first three things that satisfy the antecedent are king, queen, bishop. And we can see that if the king is stronger than the queen and the queen is stronger than the king, then in fact the bishop is stronger than the king. And you just say that for the next three and the next three and the next three. Each of those cases that satisfy the antecedent, the consequent is satisfied as well. So, true. Okay, that's the first half of the homework, and I'm going to do the second half in a separate video.